Let's explore the fundamental concepts of vectors in calculus and understand how they work. A vector is a mathematical object with both magnitude and direction, represented by an arrow from one point to another. First, let's understand what vectors are and how they differ from ordinary numbers. Unlike ordinary numbers called scalars, a vector has both magnitude, which is its length, and direction, which is where it points. Scalars are just regular numbers like 5, -3, or 2.7, with only magnitude but no direction. Vectors are perfect for representing physical quantities like displacement, velocity, and force that have both size and direction. This vector shows both its horizontal and vertical components, along with the angle it makes with the horizontal axis. There are several ways to write and represent vectors in mathematics. We can write a vector using angle brackets, like versus equals 3, 4, where 3 is the x component and 4 is the y component. We can also write it using unit vectors I hat and j hat as 3i hat plus 4j hat. Another notation is column vector form, with 3 and 4 stacked vertically. The unit vectors I hat and j hat point along the x and y axes with length 1. The magnitude of a vector tells us its length or size. For a 2D vector with components x and y, the magnitude is the square root of x squared plus y squared. Let's find the magnitude of the vector with components 3 and 4. We calculate the square root of 3 squared plus 4 squared. This equals the square root of 25, which is 5. The magnitude is simply the length of the arrow representing the vector. We can add vectors together by combining their components. Let's add two vectors, u equals 2, 1, and versus equals 3, 4. We add them component-wise. 2 plus 3 equals 5, and 1 plus 4 equals 5, giving us the vector 5, 5. Geometrically, we add vectors by placing the tail of the second vector at the head of the first, creating a tip-to-tail arrangement. Multiplying a vector by a scalar changes its magnitude but keeps the same direction. When we multiply a vector by a scalar k, we multiply each component by k. Let's multiply the vector 2, 3 by the scalar 2. We get 2 times 2 equals 4, and 2 times 3 equals 6, giving us the vector 4, 6. Notice how multiplying by 2 doubles the length but keeps the same direction. Unit vectors have a magnitude of exactly 1 and point in a specific direction. To find a unit vector in the direction of v, we divide v by its magnitude. Let's find the unit vector in the direction of 3, 4. First, we find the magnitude, which is 5. Then we divide each component by 5, giving us 0.6, 0.8. The unit vector has length 1 and points in the same direction as the original vector. The dot product combines two vectors to produce a scalar value. The dot product is calculated by multiplying corresponding components and adding them together. Let's calculate the dot product of 2, 3, and 4, 5. We get 2 times 4 plus 3 times 5, which equals 8 plus 15, giving us 23. The dot product also equals the product of the magnitudes times the cosine of the angle between them. Vectors are essential in multivariable calculus for describing curves, surfaces, and motion. Position vectors describe the location of a point in space relative to the origin. A position vector as a function of time describes the path of a moving object. The velocity vector is found by taking the derivative of the position vector with respect to time. So velocity equals the derivative of position, with each component differentiated separately. The position vector points to where the object is, while the velocity vector shows which way it's moving. Let's review the key concepts about vectors in calculus. Remember that vectors have both magnitude and direction, unlike scalars which only have magnitude. We can perform various operations on vectors, including addition, scalar multiplication, and dot product. In calculus, vectors are essential for describing motion, rates of change, and curves in multiple dimensions. Understanding vectors is the foundation for multivariable calculus, where we study functions of multiple variables.